Hey guys, welcome to the Academic Chemistry Chapter 4, Section 2, Structure of the Atom, Part 1. So today we're going to talk about the things that actually make up the atom and what makes atoms a little bit different from other atoms. We're just going to broach that topic, but really we're going to get into the subatomic particles, what they are, where they are, and what they do. In the next part of 4.2, we're going to talk about the different scientists that discovered each of these subatomic particles. So it's a good thing to have an idea of what the atom actually looks like so we can understand what the experiments did and why. So today we're going to talk about the three main subatomic particles. And when talking about the word subatomic, we're going to break it up into two pieces, sub and atomic. So if you have like a subcategory, then that's like a category within a category, right? Subatomic are pieces within the atom or within atomic atom. So here is our atom. And our atom is made up of three main subatomic particles. Now, there are other things that you might hear about if you read some more advanced physics, but for the scope of this course, we care about the three main subatomic particles. So we have the protons, the neutrons, and the electrons. And we're going to go through each one of these and the basic details that you need to know about the protons, neutrons, and electrons. But those are your three subatomic particles, those little pieces or particles that make up the atom. Okay, so for the scope of this lesson, here is what we're going to think of as what the atom looks like. Okay, so there's some stuff in the middle, and then there's all this fuzzy part on the outside that you can barely see. So the first thing we're going to talk about is the protons. And if you want to abbreviate it, just put a lowercase p with a superscript plus. And why is that a plus? Because protons have a +1 charge. Now we delegate this as +1 just to make it easy counting. So if you have one proton, you've got a +1 charge. If you have two protons, you've got a +2 charge. If you have 20 protons, +20 charge. So each one of the protons gives a +1. For the subatomic particles, these are considered large. Now, by large, they're really small. But compared to out of the three subatomic particles, the protons are the larger side. It's kind of like saying a jumbo shrimp, right? No matter how big your shrimp is, it's still small. So it's big for a small thing. So subatomic particles are pieces that make up an atom, which are so crazy small, we can barely understand how small they are. This is smaller than an atom. So even if it's a large subatomic particle, it's still incredibly, 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 incredibly small. So its mass is 1.67 times 10 to the 24th, -24th grams. So that means if you move this decimal between the actual decimal and where this 1 is, so there's a decimal, then there's 23 zeros, then 167 grams. So a fraction of a fraction of a fraction of a gram. So the proton is found in an area called the nucleus, and that is the center of the atom. So if you look at this picture, the purple is representing our protons, and it's found in the nucleus. The nucleus is just any word that means the center of something. You learned that in biology, the center of the cell is the nucleus. Or if you have a group of friends, if you have like a nucleus of friends, that core group within your broader scope of friends, nucleus just means the center. So the center of the atom, that's where you're going to find the protons. The protons determine the identity of the atom, so which element it is. So based on the periodic table, what is it? Well, it depends how many protons are in it. So all carbon atoms, for example, have 6 protons. If you ever have anything with 6 protons, it has to be carbon. It cannot be anything else, okay? All titanium atoms, for example, have 22 protons. If you've got 23 protons, it's not titanium. If you've got 21 protons, it's not titanium. 22 protons means it's titanium. So those two things are synonymous. However many protons you have, that's exactly what type of atom, and it doesn't ever change. So here we are, protons hanging out there in the center. The next thing we have are the neutrons. So if you want to abbreviate that, it's a lowercase n with this 0 up top. Now, last time we had a plus charge because protons had a positive charge, and this has a 0. What does that mean? No charge, 0 charge, okay? So I've got a joke for you. All the subatomic particles walk into a bar, and the neutron orders a Coca-Cola, and the bartender says, "Neutron for you, no charge." Feel free to laugh later. Okay, So neutrons are neutral or no charge, no charge, N, no charge. These are also large. They are the same mass as the protons. And when you get into nuclear decay, you'll kind of find out why these have the same mass. But these are also your large subatomic particles. So out of the insanely small things that are smaller than we can process, these are larger than the other ridiculously small things. These are also in the nucleus, and they provide a buffer between all the positive protons. So you've heard before that opposites attract, I'm sure, which means that like charges repel. So if you're hanging out here in the nucleus, all these purple things all have a positive charge. They don't want to be next to each other, but they are. They're all packed into the nucleus. So the neutrons just provide this buffer area to kind of be like, whoa, protons, you don't have to get too close to each other. Don't worry, it's cool, because the neutrons have no charge, so they don't interfere with any electronic interaction. All right, so there they are. And the last one we're going to talk about is the electrons. So the abbreviation for that is a lowercase e with an up high negative sign. And you guessed it, that's because they have a -1 charge. So a proton and an electron, their charges cancel each other out. If you have one +1 proton and one -1 electron, boom, no charge. All right, these have your small mass for your small things. So the electrons are unbelievably small. They basically add no mass to the atom because they're so small. It's like if you were a proton, then an electron would be like a piece of dust that you can't even see that just landed on you, right? It's so incredibly small. All right, so electrons exist in energy levels within electron clouds outside of the nucleus, and they are involved in bonding between other atoms when making compounds. They also form an electronic current or magnetic interactions, so you've really experienced electrons, like if you've ever been shocked by something, or if your hair has ever stood straight up because, you know, you held a balloon close to it or something. Those were electrons making that happen. So here they are on the outside. They're also moving crazy fast. So whenever we take a picture of an electron, it just looks like a blur. We don't actually see the electron in one spot. So you see how this is just a little bit shaded, if anything, okay? So that is called the electron cloud because it literally looks like a cloud. You can't see it. They're going so fast. So it looks all just like foggy out here. That's also a good thing to think about, for they're going so fast that it almost becomes like a solid. So most of the atom is empty space. Nothing's there. But because the electrons are going so fast, then it actually makes it feel like something is there. Think about if you look at a fan for a long time, like when a fan's circling around, it's going really fast, it almost looks like one big circle. Well, that's what happens to the electrons. So think about everything that you touch is made of atoms, right? So if you touch your desk right now, you're touching atoms. Most of what the atom is empty space. This outside part here is the majority of the atom. The nucleus is incredibly small. This is very out of scale, but I have to make it this size so you can see it. The nucleus is crazy small. Most of it is empty space with just these little electrons, and they're going so fast that that's what you feel, is those things going so fast. Let's look at another way to describe that. So if the atom were blown up to the size of a stadium, like a football stadium, so think of Lincoln Financial Field, all right? So we took this one teeny tiny atom, the thing that builds up to make your cells, those cells build up to make you, one of those things made it bloop, the size of a whole football stadium. The nucleus would be the size of a marble. That's it, a marble in the center of Lincoln Financial Field. That's how small the nucleus is, and that's where most of the mass comes from. At this scale, the electrons are still too small to see. You wouldn't even, they'd be like the size of a cell, you know, like a bacterial cell in the stadium. So if you look at this stadium and pretend this is your atom, a marble right here is the nucleus, the electrons take up this space, and there's only a few of them, which means the majority of everything that you touch is actually empty space. You're not really, there aren't really things there, but because the electrons move so fast, It seems like it is. It's a very strange concept, but it's also really cool. So that's it for your notes for the intro to the structure of the atom. Make sure you ask questions to your teacher if you have any, and we will see you in the next set of notes.